Hello, this is the Quantumized channel, and today we'll explore one of the most mysterious properties of the quantum world, electron spin. What is spin? When physicists first encountered spin, they named it precisely that, from the English word spin, meaning rotation. This was natural. Imagine a small ball spinning around its axis, like Earth rotating on its axis. But here's where it gets interesting. Electron spin is not rotation in the conventional sense. The Stern-Gerlach experiment, how it all began. In 1922, German physicists Otto Stern and Walther Gerlach conducted an experiment that revolutionized our understanding of the microworld. They took a beam of silver atoms, heated them to evaporation, and passed them through an inhomogeneous magnetic field. What was expected? If atoms behaved like classical magnets that could be oriented arbitrarily in space, we would have seen a blurred spot at the output, since each atom would deflect at a different angle depending on its orientation. What actually happened? Instead of a blurred spot, exactly two distinct spots appeared on the detector, one above, one below. The atoms separated into two groups, as if they had only two possible states, up and down. No intermediate values. This was shocking. Imagine tossing a coin that always lands either strictly heads or strictly tails. Never on its edge, never at an angle. That's exactly how spin behaves. Why spin isn't ordinary rotation. Let's examine why we cannot imagine spin as a small spinning ball. 1. Speed problem. If the electron were actually rotating to create the observed magnetic moment, points on its surface would have to move faster than the speed of light. According to relativity theory, this is impossible. 2. The electron is a point particle. Modern experiments show that the electron has no size in the classical sense. It's a point particle, which should rotate in a point. It has no surface, no edges. 3. Spin quantization. Spin always takes strictly defined values. For an electron, it's either plus 1/2 or minus 1/2 in units of Planck's constant. It's impossible to measure spin with a value of, say, plus 0.3 or plus 0.7. Only these two options. Imagine a top that can only spin at two specific speeds, neither faster nor slower. Absurd for the classical world, but reality for the quantum world. 4. Strange behavior during measurement. Here's where it becomes truly unusual. If we measure an electron spin along the z-axis and get up, then measure along the x-axis, we again get a random result. Either right or left, with 50-50 its probability. After this, if we measure spin along the z-axis again, we once more get a random result. The information from the first measurement has disappeared. It's as if you learned that a ball is flying north, then checked if it's flying east, and learned yes. But when you asked again, is it flying north? The answer became indeterminate. In the classical world, this is impossible. What is spin really? Spin is an intrinsic quantum property of a particle, as fundamental as mass or charge. It's an intrinsic angular momentum that a particle possesses simply because it exists, not because something is physically rotating. Mathematically, spin is described through an abstract state space. The mathematics of spin, how it works. Mathematically, spin is described through an abstract state space that has no direct classical analog. For an electron, this is a two-dimensional complex space where each state can be represented as a combination of two basis states, spin up and spin down. The general spin state of an electron is written as C alpha vita, where alpha and beta are complex numbers called probability amplitudes, and their squares give the probabilities of measuring corresponding spin values. The superposition principle. Before measurement, the electron exists in a superposition of spin states. This doesn't mean we simply don't know what spin it has. It means the electron simultaneously exists in both states. Only at the moment of measurement does wave function collapse occur. The system chooses one of two possible states, and this choice is fundamentally random. We can only predict probabilities. More complex experiments, sequential measurements. Imagine we've complicated the Stern-Gerlach setup. Let's pass atoms through 3 sequential devices. First device, z-axis separates atoms into up and down. We take only atoms with up spin and block down. Second device, x-axis, now we pass atoms with up spin through a device oriented perpendicularly, measuring spin along the x-axis. What happens? The beam splits again into 2 equal parts, left and right. This means that even knowing the spin precisely along the z-axis, we know nothing about spin along the x-axis. We take only right atoms and continue. Third device, z-axis again, now we measure spin along the original z-axis again. Logic suggests we selected only atoms with up spin along z in the first device, so they should all pass as up, right? Wrong. The beam splits in half again. Half the atoms show up spin, half show down. Measuring spin along the x-axis completely erased information about spin along the z-axis. The uncertainty principle for spin. This manifests a deeper principle of quantum mechanics. Spin components along different axes cannot be simultaneously precisely determined. This is mathematically expressed through commutation relations. Sx psi equals this. This isn't a technical limitation of our instruments. It's a fundamental property of nature. Spin simultaneously doesn't have definite values along all 3 axes. By learning one component exactly, we lose information about the others. Spin and magnetism. Despite spin not being classical rotation, it creates a magnetic moment, and this has enormous practical consequences. Ferromagnetism. Permanent magnets work thanks to spin. In iron, the spins of numerous electrons align parallel to each other, creating a macroscopic magnetic field. Without the quantum nature of spin, permanent magnets wouldn't exist. Classical physics cannot explain their existence. MRI, magnetic resonance imaging. Medical MRI scanners work based on the spin of atomic nuclei, mainly hydrogen in the water of our bodies. A strong magnetic field aligns nuclear spins, then radio waves flip them, and when returning to their original state, the nuclei emit signals. By analyzing these signals, detailed images of internal organs can be constructed. Spintronics. Modern electronics is beginning to use not only the electron's charge, but also its spin for storing and processing information. Computer hard drives use the giant magnetoresistance (GMR) effect based on electron spins. The 2007 Nobel Prize in Physics was awarded for the discovery of GMR. Spin and particle statistics. Spin determines the fundamental behavior of particles and groups. All particles are divided into 2 classes. Fermions half-integer spin, 1/2, 3/2, 5/2. Electrons, protons, neutrons all have spin 1/2 and are fermions. They obey the Pauli exclusion principle. 2 fermions cannot occupy the same quantum state simultaneously. Thanks to this principle, the periodic table of elements exists. Electrons in an atom cannot all fall to the lowest orbital. they're forced to fill different energy levels. This is what creates chemical diversity. Moreover, the Pauli principle explains why matter doesn't collapse. Degenerate electron gas pressure in white dwarfs and neutron gas in neutron stars is a direct consequence of Fermion spin. Bosons, integer spin, 0, 1, 2. Photons, spin 1. Higgs boson, spin 0. These are bosons. They can occupy the same quantum state in unlimited numbers. This allows creation of Bose-Einstein condensates, a state of matter where thousands of atoms behave as one quantum object. Lasers work because photons, bosons, can occupy one state, creating a coherent beam of light. Spin 1/2. Why exactly 1/2? Spin is measured in units of /2, whereas the reduced Planck constant. When we say an electron has spin 1/2, we mean its intrinsic angular momentum equals 1/2. But why 1/2? Why not a whole number? This is related to how spin transforms under rotation of the coordinate system. If you rotate the coordinate system 360 degrees around an axis, the electron's wave function changes sign to the opposite. You need to rotate 720 degrees to return to the initial state. This seems insane, an object that after a full rotation becomes minus itself. But this is mathematically rigorous and experimentally confirmed. This property is called the spinor nature of particles with spin 1/2. Experiments with single spins. Modern technologies allow manipulation of individual electron spins with incredible precision. Nitrogen vacancy centers in diamond. In a diamond crystal lattice, a defect can be created. Remove one carbon atom, creating a vacancy, and replace a neighboring atom with nitrogen. The electron in such a defect has a spin that can be controlled with laser radiation and microwaves. Such systems are used for ultra-precise magnetic field measurements, magnetometry, quantum computing, detection of individual molecules in biological systems, Penning and Pauli traps. Physicists have learned to hold single electrons in electromagnetic traps for months and measure their properties with fantastic precision. The electron's magnetic moment has been measured to 13 decimal places, one of the most precise measurements in the history of science. Quantum computing with spins. Electron spin is a natural qubit, quantum bit, for quantum computers. Unlike a classical bit that can be either 0 or 1, a qubit can exist in a superposition of both states. Where states -0 and -1 correspond to up and down spin. Advantages of spin qubits. Long coherence time. Spins can maintain quantum state for relatively long periods. Compactness. Electrons occupy little space. Compatibility. Can be integrated with conventional semiconductor electronics. Companies like IBM, Google, Intel, and many universities are actively developing quantum computers based on electron spins in semiconductors and superconducting qubits. Spin in chemistry. Why molecules are stable. Chemical bonding between atoms is possible thanks to spin. When two hydrogen atoms combine into an H2 molecule, their electrons must have opposite spins, one up, the other down, to occupy the same molecular orbital. This is a direct consequence of the Pauli principle. Two electrons with identical spins cannot occupy the same spatial state. Therefore, they form an antiparallel pair. Spins point in opposite directions. Total spin equals 0. Singlet and triplet states. When two electrons interact, they can form singlet state. Spins antiparallel. Total spin equals 0. Triplet state, spins parallel, total spin equals 1. These states have different energy and chemical properties. For example, molecular oxygen O2 in its ground state is a triplet. This explains its paramagnetic properties and high reactivity. Spin and relativity theory, the Dirac equation. Complete understanding of spin came only when Paul Dirac in 1928 unified quantum mechanics and special relativity. His famous Dirac equation naturally predicts the existence of spin 1/2 for the electron. Moreover, the Dirac equation predicted the existence of antimatter, positrons, antiparticles of the electron. This was experimentally confirmed in 1932. Spin turned out not to be a random property, but an inevitable consequence of combining quantum mechanics with relativistic physics. In a certain sense, spin is the price nature pays for reconciling these two fundamental theories. Spin entanglement, quantum non-locality. Two electrons can exist in an entangled state where their spins are correlated regardless of the distance between them. For example, if you measure the first electron spin and get up, the second electron spin will instantly be down, even if the electrons are at opposite ends of the galaxy. Einstein called this phenomenon spooky action at a distance and couldn't accept it. But experiments, especially Alain Aspect's experiments, for which he received the 2022 Nobel Prize, convincingly proved the reality of quantum entanglement. Applications of entanglement. Quantum cryptography. Absolutely secure information transmission. Quantum teleportation. Transmission of quantum states over distance. Quantum sensors. Ultra-precise measurements inaccessible to classical devices. Exotic spins. Particles with higher spin. Not all particles have spin 1/2. Particles exist with other spin values. Spin 0, Higgs boson, pions. Spin 1, photon W and Z bosons, gluons. Spin 3/2, delta baryons. Spin 2, hypothetical graviton, carrier of gravitational interaction. Interestingly, particles with spin greater than 2 haven't been found in nature. It's been theoretically shown that elementary particles with spin greater than 2 lead to causality violations or other physical contradictions. Neutron spin, dark matter detector. Neutrons also have spin 1/2, and this is used in searches for new physics. Experiments measuring the electric dipole moment of the neutron, which is related to charge distribution and spin, can help understand the asymmetry of matter and antimatter in the universe. Ultra-sensitive measurements of neutron spin precession are also used to search for axions, hypothetical particles that may constitute dark matter. Conclusion: spin as a window into the quantum world. Spin is not just an abstract mathematical property. It's a fundamental characteristic of matter that explains the structure of atoms and the periodic table, makes possible the existence of matter as we know it, underlies magnetism and numerous technologies, opens the path to quantum computing and communications, reveals the deep connection between quantum mechanics and relativity theory. Spin teaches us the main lesson of quantum mechanics. Nature at the fundamental level doesn't work like our macroscopic world. Our intuition, based on everyday experience, often fails us. The electron isn't a tiny top, and attempts to imagine it as such are doomed to failure. But the mathematics of quantum mechanics works flawlessly. It predicts experimental results with astonishing precision. And although we cannot visualize spin in familiar terms, we can measure, control, and use it. Spin is an invitation to leave classical concepts of the threshold and enter the amazing world of quantum reality, where the possible becomes impossible and the impossible becomes ordinary. Thank you for being with us on the Quantumized channel. Dive into the quantum world, and remember, reality is far stranger than it seems.